What's up, guys? Welcome back to another exciting video covering topics in the SOA's Statistics for Risk Modeling exam. Today's video is about smoothing time series. Smoothing techniques are used to reduce noise and better reveal the underlying trend in a time series. The most common smoothing technique is the moving average. The general idea is simple. Instead of using the original data points in analyses, we average them out with their neighbors so that we can better analyze the underlying trend. Let's look at the moving average formula. Here is the equation to calculate the moving average, also known as the running average. S hat t represents the smoothed value at time t, yt is the actual observed value at time t, and k is the running length average. The numerator is the sum of the previous k observations, ending at and including time t. To get the average, we divide by the window length, k. So for example, if k is 3, the moving average at time 5 is the average of the observations at times 3, 4, and 5. Alternatively, instead of re-adding everything every time, we can use the recursive form. This helps with computational efficiency, since it takes the previous average and adjusts it by adding the new point and removing the old one. We don't have to recalculate the average every time. Here is a time series with a clear trend and strong seasonality. The white dots are the raw data. Connecting them directly results in a jagged, messy line. What happens when we try to smooth this with k equals 4? Let's find out. We average the current point and the 3 before it to find the blue dot. Step forward. Drop the last one, add the new one, and again. See how the blue dot stabilizes the movement? We keep doing this. Repeating this for the whole series gives us the moving average line. Now let's try k equals 8. This time, we look back at 8 points. Notice how many more connections there are? The average is pulling from a much wider history. Smoother, but slower to react. Smoother, but slower to react. Notice how the red line is significantly smoother than the actual data. When selecting k, we need to be careful not to over-smooth the data, since it can cause us to miss important trends. All right, let's look at a simple example. Okay, so we have a time series with 6 consecutive periods. We are given that the moving average at time 5 is 21, and our window length, k, is 3. We need to find the average for time 6. Since we are given the moving average at time 5, we are going to use the recursive formula to find the moving average at time 6. We take the old average, add the new value coming in, subtract the old value leaving, and divide by k. So S hat 5 is 21. Boom. Then we grab y6, which is 27, bam. And subtract y3, which is 18, kaplow. We math the numbers out, adding 21 and 3 to get 24. Boom! Moving average calculated. Mission complete. Now that we've covered moving averages, let's dive into an extension of it, double smoothing. We'll also talk about forecasting, since that's one of the main applications of smoothing techniques. Suppose you are using a linear trend in time model to predict the future values of a time series. How can we use double smoothing to forecast the future values? Double smoothing involves 2 main steps. First, we create a standard smooth series using a moving average. This is the single smoothing formula from before. Next, we smooth that series again using the moving average series from the previous step. This is the double smoothing step. Using the difference between the smoothed series and the double smooth series at the last observed time, capital T, we can calculate an estimate of the underlying trend. To get the forecasted points, we combine the current level and the trend estimate to generate forecasts into the future. Let's visualize this. Here is our noisy data with an upward trend. The single moving average with k equals 8, represented by the blue line, smooths the noise. To get the double smooth series, we average the blue line. Let's zoom in to see how the red line is formed. We take the past 8 points of the blue line and average them to find the new red point. We slide the window forward 1 step. Repeating this process creates the doubly smoothed line. At the last observed time t, the red line lags behind the blue line. However, since the slope is a function of the difference between the blue and red dots, this difference allows us to use a linear trend model to predict the future values of the time series. Exponential smoothing builds on simple moving averages. However, instead of treating all observations in a window equally, it assumes that the most recent observations are more relevant for forecasting than older ones. The weights decrease exponentially as the data gets older, hence the name exponential smoothing. Mathematically, the exponentially smoothed estimate is represented by this formula. The numerator is the weighted sum of all past values, where the weights are decreasing exponentially. Using the formula for the sum of a geometric series, we get that the sum of the weights is 1 divided by 1 minus the weight factor. So to normalize the weights, we divide the entire formula by the sum of the weights. Similar to moving averages, calculation is easier using a recursive formula. The new estimate is simply a weighted sum of the current observation and the previous smoothed estimate. The parameter w controls the smoothing. Note that it ranges from 0 to 1. As w approaches 0, the term 1 minus w becomes larger. The estimate is mostly determined by the current observation yt. Little smoothing takes place. As w approaches 1, more weight is given to the previous estimate. A high level of smoothing takes place as the estimate relies heavily on past history. Let's apply this to the same data set from earlier and see how exponential smoothing differs from moving averages. We'll start with the calculation of the exponentially smoothed series for w equals 0.2. This means that we assign more weight to the current observation and less weight to the previous estimate. Notice how the new estimate is a weighted balance between the previous estimate and the newest raw data point. We observe that the line closely follows the raw data when w is 0.2. Repeating this recursive process gives us the full smooth line for w equals 2. Because the weight assigned to the previous estimate is low, more weight is given to the current observation, so the line closely follows the raw data. Let's see what happens when we increase w to 0.5. We observe more deviation from the raw data when w is 0.5, since the previously smoothed estimate is given more weight. With w increased to 0.5, more weight is placed on past estimates. The orange line is smoother, but deviates more from the raw data. Now let's see what happens when we increase w to 0.8. Compared to the previous two cases, we notice that the new point deviates even more from the raw data. With w at 0.8, the line becomes much smoother, but it lags behind changes from recent observations, reacting slowly to new changes. Notice how for the more recent times, the smooth line is significantly lower than the raw data, since it's still playing catch-up to the recent changes. Similar to double smoothing, double exponential smoothing is designed to handle time series data that exhibits a linear trend. If we assume our data follows a linear trend over time, we start by smoothing the raw data using exponential smoothing. Here, w is the weight parameter. Next, we smooth the smoothed series again. Then, by comparing the single and double smoothed values at the current time t, we can estimate the slope and intercept. Finally, we project these estimates forward L steps to generate our forecast. Let's visualize this with a time series with a strong upward trend and some noise. First, we compute the single exponentially smoothed series in blue. Notice how it reduces the noise but lags behind the trend. Then, we compute the double exponentially smoothed series in red. This lags even further behind the blue line. Using the formulas from earlier, we calculate the intercept and slope and project the series forward. So far in this video, we've covered calculating a slope and intercept for forecasting a doubly smoothed series. We didn't mention this for simple smoothing. When forecasting for simple smoothing, we assume that the level of the series remains constant after the last smoothed data point, regardless of what our data looks like. This is because simple smoothing relies on a weighted average of past observations. There is no actual trend calculation involved. So the best estimate of future values in simple smoothing is simply the most recently smoothed observation. So for this particular dataset, where our data seems to be increasing with time, forecasting with simple smoothing methods is probably not a good idea. Let's tackle SOA Sample Question number 46. This is a good example because it involves both simple and double exponential smoothing. It also allows us to see how forecast estimates are different for the two methods. We have a time series up to time 100. We are also given some smoothed values. The smoothing weight W is 0.8. Our goal is to find the absolute difference between F, the exponential smoothing forecast, and G, the double exponential smoothing forecast, for time 102. Before we dive into the calculation, let's figure out what pieces we need. We start with the recursive smoothing formulas. These update our single and double smooth statistics. Then, we use those statistics to determine the slope and intercept, which combine to create our linear forecast 2 steps ahead at time 102. Okay, let's dive in. First, calculating F. We need the smoothed value at time 100. We use the observation at 100 and the smoothed value at 99. The calculation gives us 96.1. Since we're forecasting for simple exponential smoothing, we assume that the level of the series remains constant after the last smoothed data point, regardless of what our data looks like. So in this case, y hat of 102 is the same as our most recent calculation of S at time 100. This gives us a forecast of 96.1, so F equals 96.1. Now for double smoothing. Our goal is to find the double smooth value at time 100 since we need it for the trend and intercept calculations. We calculate the value for time 99 first since it's needed to calculate S hat 2 at time 100, plugging in 0.8 for W, 95.1 for S hat 1 at time 99, and 89.9 for S hat 2 at time 98. Putting it all together, we get 90.9. Now we use the same formula to calculate S hat 2 at time 100. We start with the single smooth value from step 1 and combine it with the double smooth value of 90.9 to a weighted average of 91.9. Step 3, calculating trend and intercept. We need our single and double smooth values at time 100. First, we calculate the slope, beta 1. We take 1 minus W over W, which is 0.2 over 0.8. We multiply this fraction by the difference between the single and double smooth values. This gives us a slope of 1.05. Next, the intercept, beta 0. The formula is 2 times the single smooth value minus the double smooth value. Plugging in 96.1 and 91.9, we get 100.3. Now step 4, forecasting G for time 102. Since our data ends at time 100, we are forecasting L equals 2 steps ahead. We take our intercept of 100.3 and add 2 times our slope of 1.05. This results in a final forecast of 102.4. Finally, in step 5, we calculate the absolute difference. The result is 6.3. The SOA sample questions are a good reflection of what you'll see on the exam. However, this question is one of the more tedious and difficult ones, so don't worry if you don't get it right away. Not all questions are like this. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.